Covalent bonds. They're found in anything you can think of, from water to dinitrogen trioxide. Covalent bonds are usually liquids or gases in room temperature, and they have a relatively low melting and boiling points. Covalent bonds are bonds between two nonmetals that share electrons. These neutral groups of atoms that are held together by the sharing of electrons are called molecules. Here is Professor Garrett White to demonstrate this.
Thanks, Professor Chong. What's up, kids? My name's Garrett White, and let's get down to science. Okay, so picture this. These large styrofoam balls are atoms. This one's oxygen, this one's hydrogen, and this one's also hydrogen. So oxygen typically has 6 electrons, and these small styrofoam balls are the electrons. So the oxygen has 6, this hydrogen has 1, and this hydrogen has 1. Now, these atoms want to combine so that they all have 8 electrons. And for non-metallic atoms, we have to use covalent bonding. So what's going to happen is this hydrogen's going to go over here, and they're all still retaining their electrons, right? So this oxygen still has its 6, and the hydrogen still has 1, but the hydrogen's going to share 1, and the oxygen's going to share 1, and that's a bond now. And the oxygen's going to share 1 with the other hydrogen as well, and that's another bond. And this is going to leave 2 lone pairs on the oxygen, but now the hydrogen has 2 to fulfill the rule. Both hydrogens have 2, and now the oxygen has 8. What's important to note, however, is that the bonds that are holding this molecule, or covalent bonds, together is much weaker than that of metallic or ionic bonds, because there's no actual transfer of electrons, so there's no electrostatic attraction. Instead, there's just intermolecular forces, so it's much weaker.
Thank you for the wonderful demonstration, Professor White. Now, covalent bonds have 3 types of bonds: single, double, and triple bonds. Single bonds are shared between 1 pair of electrons, and they are the weakest yet longest bonds. Double bonds are shared between 2 pairs of electrons, and they are medium in both strength and length. While triple bonds are shared between 3 pairs of electrons, and they are the strongest yet shortest bonds. Here is Professor Rajarajan and Anandar to demonstrate this.
Thank you, Professor Trong. I'm
Professor
Ethi.
I'm
Professor
Zaki. Imagine a series
of
ropes.
Imagine a series of rope. What would be harder to break? 1 strand, 2 strand, or 3 strand? Well, Zaki and I are here to demonstrate.
So, if you have 1 strand of rope, breaking it is pretty easy. But what happens when we have 2 strands of rope? It's going to be a little bit more difficult, but it's still doable. But now, what happens when we have 3 strands of rope? So, as you can tell, this is going to be much more difficult to break. But nothing I can't handle.
You might be wondering how this relates to covalent bonding. Well, Zaki's here to tell you.
So with the single strand, it represents a single bond with 2 electrons. And this is the longest except the weakest bond. And with the 2 strands, it represents a double bond with 4 electrons. It has the medium length and also the medium strength. And then with the triple bond, with the 3 strands, it represents the triple bond, obviously. And it has 6 electrons, and it is the shortest but the strongest bond.
Thank you for that demonstration. When naming covalent bonds, we use Greek prefixes to indicate the number of each element. The ending of the second element is changed to "-ide". For example, water could also be called dihydrogen monoxide. For acids, we use hydro-blank-ic acid for single elements, blank-ic acid for polyatomic ions with the 8 ending, and blank-is acid for polyatomic ions with the ic ending.
Great job, Trong. Hey, Sydney, can we get off our phone in class, please? Thank you so much. Okay, so now we're going to talk about bond polarity. And this is different from molecular polarity in that it deals specifically with just the bonds between 2 atoms. So right now we have a molecule, water, And you see here there's bonds between this hydrogen and this and the oxygen, and this hydrogen and the oxygen. So what's important to note is that the electronegativity of the oxygen is significantly higher than that of the hydrogen. So if the electronegativity is higher than 0.2 but less than 1.7, it's a polar covalent bond. If it's less than 0.2, which happens in diatomic covalent bonds, then it's just a non-polar covalent bond. And if it's greater than 1.7, the bond is ionic. So what we see here is that the electronegativity of oxygen is 3.4, and the electronegativities of the two hydrogens are 2.2. When we find the difference of that, it's 1.2, and 1.2 lies between 0.2 and 1.7. Therefore, the bond between hydrogen and oxygen is a polar covalent one. So what this means for the oxygen and the hydrogen being a polar covalent bond is that since the electronegativity of the oxygen is significantly higher than that of the hydrogen, it's going to pull the electrons away from the hydrogen and towards the oxygen, and that means that this side of the molecule, the oxygen side, is going to be more negative, while the hydrogens are going to be more positive.
Alright, so what determines the molecular polarity is the Vesper shape of the molecule, the presence of the polar bonds within the molecule, and the arrangement of those polar bonds throughout the molecule.
Now, you might be wondering what the Vesper theory is, and why molecular polarity depends on it. Well, the Vesper theory predicts the shape of molecules based on the electrostatic repulsion of the electrons. Here is Professor Garrett, Zaki, and Iti to demonstrate this.
These balloons represent atoms, while these styrofoam balls represent lone pairs. And in this Vesper shape, since it only has one bonding region and 0 lone pairs, it is linear. If you add a third atom on this side with 2 bonding regions and 0 lone pairs, it'll still be a linear shape.
Alright, so if you have 2 bonding regions and 1 lone pair, it will be bent, and if you add another lone pair, it would be bent but with a lesser degree.
Imagine the center of this model as the central atom. And as you can see, there is 3 bonding sites, and down here 0 lone pairs, which makes this trigonal planar. If you add a lone pair down here, it's going to make this model trigonal pyramidal.
This Vesper shape is tetrahedral. It has 4 bonding regions and 0 lone pairs.
No gold on my neck, that's a medal. Now you wanna talk about only non-metals.
Ay, electron shed on like Genghis Khan into wires that can't be drawn with a single, double, triple bond. More bonds mean more strength, but less bonds mean more length. With 2 non-metals, a bond is made of charge and will degrade. Ay.
Crank down the melting point, pull down the boiling point. In water, they stay joint, never disappoint.
Diatomic elements are quite stable. To find them, look at the periodic table. Pick a 7 or use off crinkle. Exist in pairs but can't be single. Covalent bonds use a Greek prefix, not by using any cross fix. Electronegativity determines bond polarity. Difference less than 1.7, 1.2, we're chilling like Devin. That's for polar. How about the opposite? Less than 0.2, non-polar, we got it.
Let's go on a joyride. Covalent or ionic, you pick a side. You chose francium, that's such a disgrace. You know we gonna blow up in your face.
Vespers used to predict the shape. Electrons repulse to find an escape. Bonds keeping together like a tape. Not all heroes wear a cape.
Usual charts, pick a side. Greek or Roman, pick a side. Non-metals or metals, pick a side. Now I'ma take you aside. You better share and not hide. Stay joined, don't divide.
Stay together in water, so sweet, I won't bother. I'm a teddy bear, always sharing. You want me, I'm so caring. Ay. Let's go on a joyride. Covalent or ionic, you pick a side. You chose francium, that's such a disgrace. You know we gonna blow up in your face. Yo, that's why we on the covalent side. Ionic bonds, you might as well have died.